Okay, so welcome back to another video. So today's video is pretty much just a simple question. What is the antiderivative of secant x dx? Or what is the indefinite integral of secant x dx? Now, it just sounds like a simple function, secant x dx, so you're thinking you could just use your basic rules. You probably might be thinking, oh, maybe the integral of secant x is tangent x, but be careful there. The derivative of tangent x is secant square x. So otherwise, if there was a square, the number 2 beside it over there, then this video would have been like short, super short, that it wouldn't even be called a video to begin with. So yeah, there's no exponent that corresponds with this trig function. So this is actually, it's not as complicated as you think, but the work from here is going to be tedious. And I say that because a lot of the stuff is, specifically we'll be dealing with not only rewriting a bunch of, using a bunch of trigonometric identities, but also involving with stuff with u-substitution and partial fractions and everything with stuff dealing with like natural logs. So there's just a lot going on for just this simple trigonometric function over here. But in the end, there is a closed form that does exist for this indefinite integral over here. So with that, let's actually jump in. So let's actually rewrite our secant x. So we know that from our trig rules that that's equivalent to 1 divided by cosine of x dx. Okay, so how about now what I can do is, how about I multiply and divide a cosine of x. So basically that's just equal to 1, so nothing's really changed. No, the equation still stays, the integral still stays the same, but it's more of along the lines of rewriting some of our rules of the trig identities really. So we have cosine of x and then divided by cosine square of x dx. Now we know that cosine square of x using another trigonometric identity that's actually equivalent to 1 minus sine square of x dx, right? So now integrating this is simple because you can actually use u-substitution. So we can let u equals sine of x, then du will equal cosine of x dx. Then due to substitution, we have that cosine dx will cancel. This will just be 1 on the numerator. And then in the denominator, we have a 1, then minus u square du. This coming from here, you can actually split the denominator from using partial fractions. Simply, this is actually, the denominator comes down in the form of a difference of squares. So we can actually decompose this to write that as 1 divided by 1 minus u, and then multiply with 1 plus u du. We can actually solve this indefinite integral by using partial fractions decomposition. So what that says is that if we just focus on just our integrand, so 1 divided by 1 plus u, and then 1 times 1 minus u, then we can define some constant for the numerators a as the sum, so this will be 1 plus u, then we add this with some constant b, and then 1 minus u. And you know how to do solving the partial fractions. Well, if anything, I can actually just show the work here. This will be quick, so I'll just do the butterfly method. So this will be 1 minus, or a times 1 minus u, then we add this with b times 1 plus u, and then we set that equal to the numerator. So in this case, if we let u equals positive 1, so that means we have a minus, or 1 minus 1, then plus b 1 plus 1 equals 1, and I'll actually do the other one over here. So this time if we let this u be negative 1, so we have that this is 1 minus 1, then plus b is 1 plus minus 1 equals to 1. You'll see that if you solve this for your constants a and b, you're going to get that both of them are actually equal to 1/2. So we'll just plug everything this back into here. So how about this? Now let's actually define our integral that we're actually going to integrate. We're just going to call this capital I. So capital I is equal to 1 minus, or 1 divided by 1 minus u squared du. Therefore, we actually showed that this is 1 divided by 1 minus u, and then times 1 plus u du, where we showed that if we decompose the using the partial fractions decomposition, we get that this is just 1 over 2, then divided by 1 plus u. Then we add this with 1/2 divided by 1 minus u du. I can factor out the 1/2 and also using linearity to split this into two integrals. So we have 1/2, then multiply with the integral of 1 divided by 1 plus u du, and then add this with the integral of 1 divided by 1 minus u du. And then what I can do from here is I can actually multiply the 2 to both sides. So this time we get double the quantity of I, and then equals our integral over here. So this is actually easy to compute, which you know from your rules that this is actually just the antiderivative of this is just the natural log. Over here, this is using u-substitution. Well, same thing with natural logs, of course, but this time this will be minus. So then that means from over here we have that this is the natural log of, I'll just write the absolute value. In this case, we're dealing with positives, so this is 1 plus u. And then over here, this is going to be minus the natural log of 1 minus u, the absolute values, of course. This is equal to 2i. Now from here, we can actually just use our rules of natural logs to combine this under under a single logarithm. So this is the natural log of, see, we have the absolute value, so this is 1 plus u, and then divide by this by 1 minus u. Then we can put this back for u, so therefore that's just equal to the natural log of 1 plus sine of x, simply because our u is right here, and then divide this with 1 minus sine of x. Things may look like it can't get any simple from here, but it actually can. When I say that, what we can do is I can actually, inside our input for the natural log, I can actually just multiply and divide 1 plus sine of x. So that means natural log, if I multiply the 1 plus sine x to both the numerator and denominator, so then on the top I don't really have to like FOIL this out. I can actually just put in as a quantity, really. So it's just 1 plus sine of x square. And then on the bottom, it's a, let's see, this is 1 plus, so this is actually a difference of squares here. So this will be 1 minus sine square of x. And you can actually rewrite this over here. You could just replace the 1 minus sine square of x with cosine square of x. That's one of our identities. So let's see, 1 plus sine square of x, then square, or 1 plus sine of x and then square, quantity square. And then this will be cosine square of x right here. Okay, so you see that, you notice that both for our 1 plus sine of x and then cosine square of x, there's the exponent, the number 2, right? So I can actually just say that the whole input for 1 plus sine x divided by cosine of x, and then raised to that power 2, using natural logs, I can move that 2 to the front. But not only that, I can actually divide 2 to both sides from here, so that will just be left with just the singular capital I on its own. And so we're left with just the natural log of 1 plus sine x, and then divided by cosine of x. And we can actually simplify this even further using our trig laws. So right over here, they share the same denominator with the whole sums on the numerator. So that means I can actually write this as 1 over cosine x and then plus sine over sine of x divided by cosine of x. So really, the final answer, we're actually pretty much done. So 1 divided by cosine of x, that's secant square of x, and then sine of x divided by cosine of x, that's just tangent x. And we are done. Don't forget your c, since this is an indefinite integral. So there we have it, like so. The indefinite integral of secant of x, not secant square x, secant x is equal to the natural log of secant x plus tangent x, and then plus a c if you're actually doing indefinite integrals. If you're doing definite integrals, then you would have a bound, then you could evaluate this as some finite value. So yeah, that's pretty cool if you ask me.